Hello everyone, welcome to the live problem solving session for the course Material Characterization, which is being taught by Professor S. Shankaran of IIT Madras. The course ID is NOC 26mm43. This is the live problem solving section for the week 4 of the course. My name is Mangal. I'm a research scholar in the Department of Electrical Engineering at IIT Bombay. The course instructor is Professor S. Shankaran, who is an associate professor in the Department of Metallurgical and Materials Engineering at IIT Madras. The course plan for week 4 is Introduction to Scanning Electron Microscopy, including all the types of electron optics and operations. So this session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So I will first give you an overview of the topic. So these are AI generated slides. So don't take them on face value. There might be some wrong content in there. so so first is the difference between photon optics and electron optics. So in a photon optics, we have so the parallel rays are focused at a point using a glass lens, and the principle for this is refraction. Whereas in electron optics, the focusing is done through magnetic coils, and so the principle is basically when electrons are moving in a magnetic field, a Lorentz force is applied on them, which is F equals to Q V cross V. Which so due to the since it's a cross product, the force is perpendicular to the electrons, and which is perpendicular to the movement of electrons as well as perpendicular to the magnetic field, and hence this causes the electron to move in circles in here inside the magnetic field. And since they already have a velocity, so these circles form an helical paths, and as they go further along, their as they come out of the magnetic field, they all the all the electron paths are rotated, and they get focused on a point. But why go for electron optics? Why go for electron microscopy, and why not stay at photon optics? The main reason is that we want to so the resolution in electron optics has a limit of around 100 to 100 nanometers. We cannot go below that too. So because of the wavelength of the optics, wavelength of light. So if we want to go smaller, we have to use finer wavelengths. And for that, we have to go from the visible spectrum to the high energy electron physics. So the electron also follows the Snell's law, but here But here the Snell's law, the law for electrons is slightly different. Here the it is given as a instead of velocity or refractive index, instead of refractive index, it uses potential difference. So your sine r by sine I is equal to square root of v1 by v2, where the v1 and v2 are potential in each regions, and it can do both refraction as well as reflection. So this reflection is the total internal reflection. So what? So for this, so due to this, we use electrostatic lenses. So this is a unipotential design where you have a region ground region, and in the middle you have a high potential region. So electrons come inside this region. They get so so when they go from a lower potential to a higher potential, they their angle changes, and then when they go from high potential to again low potential, their angle changes again, and that that gives a path difference to this, and creates a focusing point. So the mechanism is a cylindrical field acts as a converging lens for a divergent electron beam. So the electron beam was divergent, and this cylindrical field now made it convergent, and it is unipotential because the initial and the final beam are both at the same potential, and only the middle has a different potential. So the focal length equation here will be 1 by f equals to 3 by 16 integration of z1 is z0 vc by v naught square dz, where vc is the central potential and v naught is the outside potential. So you can see, so in a glass, once a glass lens is made, the focal length is fixed, but here you can change the focal length by changing the middle potential. Now that was electrostatic lenses. Now this is electromagnetic lenses, where the current through these coils creates a magnetic field which exerts a Lorentz force perpendicular to the electron direction and perpendicular to the magnetic field, which creates an helical path. And once it comes out, it gets focused at a central point. So, so in light optics, the image is always inverted. That is, it is 180-degree inverted. But in electron optics, it will be inverted plus rotated. due to this due to this rotation inside the magnetic field, and by changing the current in the magnetic field, you will change the focus, and that will change your rotation angle. So here 1 by f is proportional to integration of h square dz by v naught, where h square is the magnetic field magnetic field, So how an electron optical system looks like. So the heart of the system is this thing called the column. So which starts with an electron gun, which is the source, which then goes into a condenser lenses. So the purpose of the condenser lens is to regulate the spot size. Then you have objective lenses whose function is to focus the light. Then you have projector lenses which are used to change the magnification of the image. So these are similar to how you have in a normal optical microscope. You have your lamp, uh, which is your light source. Then you have a condenser to regulate spot size. Then you have an objective to focus on the specimen, and to so the instead of projector lens, the objective itself changes your magnification and to view. So then you also have detectors to collect the scattered electrons, and here for that you have an eyepiece for viewing an optical. So next we come to electron gun, where which is used to generate the beam. So here you have a filament which is your cathode, and you have an you have a anode aperture below. So the so the potential difference between your cathode and your anode is called your accelerating voltage, and that is used to determine the speed of your the and speed of your electrons. Now there are several ways of generating electrons from your filament, which we will discuss. And you also have this thing called a Venner cylinder, which is or a grid cap, which is used to control the amount of electrons being ejected, and it is used to compress the emitted electrons into a source. Then you have your condenser lens, which are used to regulate the intensity. so there, so after the condenser lens, there's an aperture which. So if your condenser lens regulates your intensity of the beam and the spot size, so the focal length formula for the condenser is given as Fc equals to eta c b naught by n square I square. So by increasing the current in the coil, you can reduce the focal length. So if you have a low current, the focal length will be large, and the and all of the current will go into the aperture. But if you have a high current, the focal length will be lower, and the focal point will be much before the aperture, and most of the light will be blocked by the aperture, and very few light will go into the aperture. So it will reduce the beam current going into the aperture. Then you have your objective lens, which is used for focusing. So in here you have a component called a pole piece, which gives which concentrates the magnetic field into a tiny gap, and it is used for minimizing spherical aberration. Then we come to different types of emitters. So first you have thermionic emitters. which can be tungsten hairpin or lanthanum hexaboride. So, so tungsten is robust and low cost, and it gives around brightness of around 10 per 5 ampere per centimeter square, whereas lanthanum hexaboride has a higher brightness and a longer life, but is also much more expensive. Next, you have field emission guns, which so they have two anodes. The first anode is used to extract electrons via tunneling instead of heat. So in thermionic emitters, what happens is we heat this filament, and that leads to ejection of electrons, emission of electrons from the filament. Here, instead of heating the filament, we use tunneling to extract electrons. So the extraction is this is known as extraction. Uh, First anode is then used as extraction voltage, and then second anode is used for your acceleration. The advantage here is that this has an extremely fine crossover. Crossover is the point where the emitted electrons meet, and a very high coherence. So they have a very high resolution. So now the field emission is also of two types: Schottky and cold. In Schottky, it's a combination of tunneling and heating, whereas cold is completely at room temperature. So the brightness is highest with cold field emission, and the source size is the smallest here. So you can see for for thermionic emitters, you don't need a very small source size. Source size typically in microns, whereas for field emission, the source sizes are also in nanometers, and the energy spread is also much lower compared to 1 to 3 ev to zero point 0.3 ev. So that reduces your aberrations, and hence the overall resolution increases. So you have a parameter called brightness, which determines image quality at high magnification, which is your beta equals to 4 IP by pi square d squared alpha square, where I is your current of the beam, alpha is your convergence angle, and d is your spot size. So d is your crossover diameter, where your electrons cross over after coming out of the source, and alpha is your angular spread of the beam. So the goal is to have high beta, to have higher resolution at higher magnification, and so now we come to aberration. So first is your spherical aberration. The problem is that the lens fields are imperfect. The peripheral fields, that is fields closer to the edges of the lens, have stronger fields compared to the center, and this results in different focal points for peripheral rays and axial rays. So, so since they are not focusing at the same point, the so and we don't get a point. Instead, we get a disk, which is called disk of least confusion. and the radius of this error is grows with cube of aperture angle, which is delta sp is equals to 1 by 2 cs alpha cube. So if we want to reduce this error, we must reduce the beam with an aperture to reduce alpha, but by reducing the beam, you sacrifice your signal intensity. So next would be chromatic aberration and astigmatism. So chromatic aberration is caused by energy spread in the beam. So in photon optics, the chromatic aberration is caused due to difference in wavelengths. Here it is caused due to here the how a wavelength of an electron is calculated. It is calculated using de Broglie principle, which is h by p, which is h by momentum. So and momentum is calculated as your from your energy. So so the energy spread in the beam will cause basic difference in wavelengths of your electron, and that will cause your chromatic aberration. So and it is also caused by the fluctuations in lens current. So the lens current might not be constant, it will be fluctuating. That will also cause, so the error for chromatic aberration is calculated as cc, which is your coefficient of chromatic aberration, alpha, which is your acceptance angle, and square root of del v by v naught square plus del I by I square. Then you have astigmatism, which is caused by machining errors or dirty apertures, which create non-symmetric fields, which are elongated in one direction and not in the other. So for that, stigmators are used, which which force the which apply a correcting field to force the beam back to circularity. Now, next type of error that you can get is space charge effect. So this is a unique case because this effect does not happen in photon optics. So the space charge effect happens because electrons are repelling each other, but photons do not repel each other. Hence, this effect does not exist in photon optics. Only in electron optics it exists. So so at the focus point, the electrons are closely packed and they are mutually repelling each other. So what will happen is that the electrons will start spreading at the point of contraction, and this will effectively reduce the accelerating potential, and the electrons will lose velocity. So the the solution for this is to use very high voltages. If we use very high voltages, what will happen is that electrons are moving very fast, so they do not have time, they do not get much time to affect each other. also use lower beam currents, because lower beam currents means less number of electrons per unit time. So there are not many electrons at this together coming together at the same point to repel each other. Now, apart from that, the specimen will also have some errors like contamination. It can react with the beam, and it has thickness variation, which will lead to in scattering errors, differences. So that also has to be kept in mind. Now you have your diffraction limit. So just like Rayleigh criterion and Abbes criterion in photon optics, here also the diffraction is limited by uncertainty principle, and that is given by delta equals to 0.61 lambda by alpha. But you can see, if if we assume 100 kilovolts and alpha is 0.003 radians, the diffraction error comes out to be around 7 angstroms, which is much smaller than what you get by your Abbes criterion or Rayleigh criterion for photon optics. So this is the baseline limit, and once you add other aberrations, your final resolution will be higher. So total resolution, which is given by your optimum resolution, is given as square root of your diffraction limit plus spherical aberration contribution plus chromatic aberration contribution. And once you put all of them together, so if you put the formula for that, it will get Cs alpha cube and Cs alpha del V by V naught. So you have to balance your aperture angle versus your field strength to get optimum optimum to get minimal disk of least confusion. So what is the benefit of using a scanning electron microscope, or an electron microscope over why use an electron microscope? So if you take up any polished surface and view it with your naked eye, you will see it is very shiny and smooth. If you bring it under an optical microscope, you will find there are some scratches and markings on the surface. But if you take it under an scanning electron microscope, you will find that the true landscape of hills and valleys, and you will be able to determine the 3D topography of your surface. So what exactly happens when an electron beam hits your sample? So this is your specimen. When an high energy electron beam hits your sample, it results in multiple signals. So the one of the main signals is your backscattered electrons and your secondary electrons. So backscattered electrons are electrons So they are scattered by the nucleus of your nucleus of atoms in your specimen, and secondary electrons are repelled by the electrons. So the electrons, the incident electrons hit the electrons, the valence electrons inside of your atoms, and eject those electrons. So they are called your secondary electrons. Next, next signal would be your X-rays. So since this scattering is happening, there will be some loss of energy, and thus loss in the energy of the electrons, and that loss of energy is is given out as radiation. That will be your visible light and your Brimstone long X-rays, depending on how much scattering is happening. And other than that, there there would be electron transitions within the atom, which will result in your characteristic X-rays, that are your K alpha, K beta points, and also it will result in Auger electrons from your light elements. So these are all the signals that come out from when an electron beam hits your specimen. So now there are two types of electron microscopes: TEM, which is your transmission electron microscope, versus SEM, which is scanning electron microscope. So in TEM, a thin sample is used, and we detect the samples which are scattered, which go through your specimen. So the detector is below your specimen, whereas in SEM the detector is in the same plane as your column, and it is reading backward scattered electrons. Now for now, if you want to decode your topography, which is your how your surface looks like, that is mainly done by secondary electrons as well as backscattered electrons. So the amount of electrons, um, scattered electrons, will depend on your surface topography. So more electrons will escape from your edges and slopes compared to your depressions. This will result in a 3D like image with shadow effects, and it will have a larger depth of field and superior lateral resolution in topographical mode. Actually, it will have a smaller depth of field, not larger. So one difference in the in photon optics and laser and electron optics is called demagnification. So in photon optics, we focus on magnification, but here we are demagnifying. So our source is in microns. So we just studied thermionic sources; they are in microns. So the laser column are used to demagnify that micron level source into a spot size which is few nanometers across. So this is called demagnification, which is done by magnetic lenses. So now you want to take the image of a sample. So image is taken at multiple points, not a single point, right? So for that, we use something called scan coil. So what a scan coil does is it it deflects your beam across different regions of your sample. Now there are different type of spectroscopy analysis that you can do on that you can also do. One is called EMPA, electron probe microanalysis, which is used to read the characteristic X-rays which are emitted from our atoms, and so the information is obtained from a localized region, and this gives us the compositional information of that region with both qualitative and quantitative analysis. Then there are two types of spectrometers used, which are EDS and WDS. So EDS is your energy dispersive spectrometer, and WDS is your wavelength dispersive spectrometer. So in the energy dispersive spectrometer detects the difference in energies, and it can detect elements which are greater than four atomic numbers, four which have an atomic number greater than 4, and it is best for major elements, that is elements which are present greater than 10%, and it is very fast, and it connects simultaneously for all energies. Whereas wavelength dispersive spectrometer, so an X-ray shining on the so X-ray shines on a crystal and it creates diffraction according to Bragg's law. So it is very sensitive. It can detect minor as well as trace elements which are below 0.1 weight%, and it can also detect low atomic numbers like boron, carbon, nitrogen, oxygen, and it has a higher spectral resolution. Then for structural analysis, we use something called EBSD, which is electron backscatter diffraction. So, so it is primarily studied using backscattered electrons only, and the backscattered electrons create a pattern known as Kikuchi pattern, and that pattern is then studied to determine the crystal structure as well as grain orientation. It can determine the phase of your sample, as well as there are if misorientations across grain boundaries are there, and this is very surface sensitive technique. So if you see the performance of your of a SCM, it has a resolution within 1 to 5 nanometers, which is over 100 times better than your microscope of an optical microscope. And it also has a very high magnification range, so it can go from 10x all the way up to 300,000x. So and very easily adjustable magnification ranges. So it has high spatial resolution, it has a large depth of field for 3D like appearance, and it has magnetic, and it has different contrast modes for different types of analysis, and it is operated under very high vacuum like 10 per minus 4 pascals. So it can be used for imaging, for structural analysis, as well as for compositional analysis. So, so there are two types of primary electrons, secondary electrons, and backscattered electrons. So secondary electrons are of lower energy. They are they are generated only at the surface level, not at the deeper level. whereas backscattered electrons are generated deeper in the level and they are scattered from atomic nucleus, so they are sensitive to atomic number, and therefore they are able to provide compositional contrast. So you have something called, for detecting these electrons, you have called something called Evenhart-Thorne detector. So which has two types of collection grids. One is set at a bias of 300 volts, one is at a bias of minus 100 volts. So what happens is the 300-volt collection grid will allow both secondary electrons and backscattered electrons, whereas the minus 100 bias electron will only allow your backscattered electrons. It will block your secondary electrons. And then you have scintillators, which are then which take your electrons into a which we have scintillators which convert electrons into photons, and the photon and the number of photons generated are then counted using a photomultiplier tube. So our secondary electrons are used for topography, where they're so here the edges appear brighter due to edge effect, since the exposed volume is higher, and the backscatter electrons are used for Z contrast, that is higher atomic numbers will scatter strongly, so they have, because they have larger nucleus, so they will scatter strongly, so they will appear bright, whereas lower atomic numbers will scatter weakly, so they will appear dark. Now the beam can be controlled in four ways. One is your accelerating voltage, one is your probe current, which is a beam current, one is your convergence angle, and one is your probe diameter, that is your spot size. And balancing these four is required for getting best image quality. So one would be your probe diameter versus current. So if you have a lower diameter will result in a higher resolution, but it will also have lower current, which will result in lower signal, and that will reduce your signal to noise ratio. So you will have a grainier image. Whereas for if you increase your current and probe diameter, you will have a very high signal, but your resolution will be very poor. So a balance has to be maintained. Next would be your oscillating voltage. So higher voltage is not always better because it increases penetration. So this is your penetration depth. So if you increase your voltage, your penetration depth will increase. And if you want to get surface level information, you will not be able to get that with higher accelerating voltage. Next would be your working distance, which is so if you have a shorter working distance, your convergence angle will be higher, and you will have a higher resolution but smaller depth of focus. If you want higher depth of focus, you will have to increase your working distance, but that will result in a lower convergence angle, and that will result in lower resolution. So you have to optimize for according to your requirements. Next will be your aperture size and convergence. So if you have a larger aperture, you will be able to have higher currents, but that will also but larger aperture will also allow for more uncorrected uncorrected beam to go in, so the aberrations will be higher, but you will be able to get shallower depth of focus due to larger alpha. But if you have a smaller aperture, your current will be lower and your aberration will be minimized, but your depth of focus will be higher. So you can how to control spot size and beam current. So if we increase the condenser lens current, it will it will result in shorter focal length and higher divergence angle from the condenser lens, and then into the and because of that higher divergence, the current entering the next lens will be reduced, and that will result in a smaller spot size, but it will also reduce the signal to noise ratio, resulting in grainier images. So this is how your resolution can be determined, and for optimum aperture angle, the formula will be kcs 1 by 4 lambda 3 by 4. So if your goal is surface detail, you should go for lower accelerator voltage to minimize penetration. For higher resolution, you should go for shorter working distance, high beam current, high high condenser lens current, and smaller probe diameter spot size. For 3D topography or depth, you should go for longer working distance to increase depth of focus, and plus smaller aperture to increase your depth of focus. For compositional contrast, you should go for higher accelerator voltage to have better penetration, plus backscattering detector because that detects your composition. So now I will be showing you some questions. The portion of electron current that leaves the gun through the hole in the anode is called beam current, emitted current, probe current, none of the above. If you have the answer, you can speak it or type in your chat. So the correct answer would be beam current. So emitted current is the current that is getting emitted from your source, but not all of that is going into your column. That is the current. The current inside your column will be your beam current. That is the current that is coming out from the anode, and the probe current is the current that is falling on your sample. In an electromagnetic lens, The magnetic field exerts force on a moving electron in a direction perpendicular to the direction of field, perpendicular to the direction of propagation of electron, parallel to direction of propagation of electron, perpendicular to both direction of field and direction of propagation of electron. That is correct. The answer will be D, perpendicular to both direction of field and direction of propagation of electron. Space charge effect is minimum when dash is used. High voltage and low beam current, low voltage and high beam current, none of the above. That is correct. The answer is A, high voltage and low beam current. Crystal structure and grain orientation of the specimen are obtained from dash angle, dash signal, SC, BSC, X-rays, Bremsstrahlung X-rays. So the answer to this will be B, backscattered electrons. So SC is secondary electrons which are used to give your surface morphology. X-rays gives you elemental analysis. Bremsstrahlung X-rays are just background radiation, and BSC backscattered electrons are have the information of your crystal structure and grain orientation. Increasing the working distance leads to dash spot size and dash the image resolution. Smaller and degrades, smaller and improves, larger and degrades, larger and improves. The correct answer would be C, larger and degrades. So the if you increase your working distance, you will lead to a larger spot size, and that will result in a degraded resolution. Which of the following option is wrong if we want to increase the brightness in an electron microscope? Increase the cathode emission current, decrease the gun crossover diameter, decrease the divergence angle, increase the voltage, none of the above. So the correct answer would be E, none of the above. So the brightness is given as 4I by pi square alpha square d square. So if you increase your cathode emission current, your brightness will increase. If you decrease your gun crossover diameter, your brightness will increase. If you increase your divergence angle, your brightness will increase. And if you increase your voltage, then obviously your brightness will increase. So all of these options are valid if you want to increase your brightness. So the wrong option, none of them are wrong. So the correct answer is E, none of the above. So you have W secondary electron, X backscatter electrons, Y X-rays, Z Auger electron. And then you have P imaging, Q crystal structure, R compositional analysis, and S detection of very light element. So you have to match with those. So you have to tell which is the correct. WP, XQ, YR, ZS, WQ, XR, YP, ZS, WR, XQ, YS, ZP, WS, XR, YQ, ZP. That so the so the correct answer is A. So the secondary electrons are used for imaging. Backscattered electrons are used for getting the crystal structure. X-rays are used for compositional analysis. To, and Auger electrons are used for detection of very light elements. Which of the following is not used for spectroscopy analysis? EDS, WDS, EPMA, Auger electron spectroscopy. None of the above spectroscopic technique is correct. All of the above spectroscopic techniques are correct. That is correct. The answer would be F. So EDS, WDS, EPMA, Auger electron spectroscopy, all of these are spectroscopic techniques that are used inside an SEM. So the correct answer would be F. For a constant focal length, what could be the expected value of depth of focus for an electron microscope working at magnification M if the depth of field of this microscope is X? So the correct answer to this would be A, m square x. Choose the incorrect option. Statement 1. Image is always rotated by a certain angle when the electron passes through an electromagnetic lens. Statement 2. Due to Lorentz force, electron travels in helical paths. Statement 1 is correct only. Statement 2 is correct only. Both are correct and 2 is correct explanation of statement 1. Both are correct but 2 is not the correct explanation of 1. So the correct answer would be C. Both are correct and 2 is correct explanation of 1. So due to Lorentz force, the electron travel in a helical path. So that results in rotation of the electrons inside the lens. So when they come out of the lens, they are rotated by a certain angle, and that is why the image is rotated when electron passes through an electromagnetic lens. So both are correct, and the 2 is the correct explanation of 1. So C is correct. For thermionic emission, which of the statement is correct for the quality of source? Melting point of source material should be high. Work function of the material should be low. 1 is correct only, 2 is correct only, both are correct, and 2 is correct explanation of 1. Both are correct, but 2 is not the correct explanation of 1. So the correct answer to this is D. Both are correct, but 2 is not the correct explanation of 1. So for thermionic emission, you want a high melting point material because so that the material does not melt at high temperatures, and you want your work function to be low so that the energy loss in extracting the electron from the material is very low. So both are correct, but both are independent statements. So the correct answer would be D. Which of the statement is correct for field emission guns? Field emission FEG can work at room temperature. Tip radius should be very sharp. 1 is correct only, 2 is correct only. Both are correct, and 2 is correct explanation of 1. Both are correct, but 2 is not the correct explanation of 1. So the correct answer for this is D. Both are correct, but 2 is not the correct explanation of 1. So, so there are cooled field emission guns which work at room temperature, and because the because field emission gun works due to tunneling, they need a very sharp radius. So again, both statements are correct and both are independent statements. So the correct answer would be D. Field emission gun source contamination can be cleaned by statement 1 by heating the tip to evaporate the contamination. Statement 2 by flashing the tip. 1 is correct only, 2 is correct only, both are correct, and 2 is correct explanation of 1. Both are correct, but 2 is not the correct explanation of 1. So the correct answer here would be D. Both are correct, but 2 is not the correct explanation of 1. So the contamination can be removed by heating the tip to around 5000 Kelvin to evaporate the contamination, or it can be done by flashing the tip, which means reversing the potential applied to the tip, and so that will reverse the effects of forward potential and it will detach the layer of atoms from the surface. So both are valid methods and both are independent methods. Answer correct answer would be D. If the strength of condenser lens increases, the probe diameter dash decreases, increases, remains same, no relation with strength of condenser lens. The correct answer would be A, decreases. So, so if the strength of condenser lens increase, it will result in a higher divergence angle before the aperture. So, it will reduce the amount of electrons going into the aperture, and that will lead to a reduced probe diameter. If we increase the condenser current, what will happen to the final probe current? Increase, decrease, remain same, no relation with condenser current. So the answer to this would be B, it decreases. So, so your probe current and your spot size both are connected. So lesser the probe current, lesser will be your spot size. Higher the probe current, higher will be your spot size. So if we inc so if you increase the condenser current, you are increasing its magnetic field. That is, you are making it stronger. So so let's say this is your condenser current. This is your condenser lens here. So if you have a low low strength condenser, that is your condenser current is low. So what will happen is your focal length out of the condenser will be high. So if this is your aperture, let this is your aperture, then if you have a lower focal length, then your beam will converge inside your aperture, and so that would mean almost all of your light is going through your aperture. So you'll have a higher current, and a higher current means a higher probe diameter. So because both are proportional. Your probe diameter and your probe current are linearly proportional, not linearly, they are proportional. So higher probe current will mean higher probe diameter. So now if I increase the strength of my condenser current, I will reduce my focal length. So now my focal length will look something like this. So if you see now if you see, so now if you see, most of my current is falling on the closed portion of my aperture, and very few of my current will go pass through here. So I will have a reduced current, and that will reduce my spot size or probe diameter. So hence in both the cases, inc increasing the strength of the condenser or condenser current means the same thing. My probe current and probe diameter both will decrease. What type of signal will be used to get the maximum contrast as shown in the figure? Backscattered electron, sorry, secondary electron, backscattered electron, X-ray diffraction signal, phonon scattering. So the correct answer will be backscattered electrons. So you can see the X-rays are used only for X-rays are not used for imaging, they are only used for elemental analysis. For imaging, secondary electrons and backscattered electrons are used, and the contrast in secondary electrons comes due to surface morphology, and contrast in backscattered electron comes due to atomic mass difference. So if you see here, this is a the reaction the reaction vessel is very deep here, so we won't get much contrast from secondary electrons since the penetration is deeper. So to get maximum contrast, we will have to use backscatter electrons, which will be able to give contrast due to atomic mass difference. A polymer or powder sample properly coated, operating at 20 kilovolts, is excessively charging during secondary electron focusing. How the operator can take proper imaging? The operator should reduce the EST kV value. The operator should change the operating mode. The sample can't be imaged. So the correct answer to this will be A. So what happens is, so when you are doing electron microscopy, you are in secondary electrons, you are ejecting electrons from your sample. So that will lead to so that will create a positive charge in your sample, and that positive charge will affect your imaging. So that is called your charging. So So to take proper image, you want to reduce charging, and for that you want to reduce the amount of electrons being ejected, and that can be done by reducing the accelerator. So the voltage of the electrons, that so EST means your accelerator voltage in electron microscope. So reducing EST value means you are reducing your accelerator voltage. So the electrons have lower energy now. So they will, so due to have, since they have lower energy, they will they will they will reduce the number of electrons ejected from the sample. A fractured sample micrograph is shown in the figure. What kind of signal was used for analyzing the sample specimen? Secondary electron, backscattered electron, ion beams, visible light. So the correct answer here would be A, secondary electrons. So to, because this is surface level imaging, so for take fractured surface images, you you want to take secondary electron imaging, because they only take the surface depth from 3 to 50 nanometers, not very deep. So they are able to properly give your surface morphology. The figure shows a contrast of GaN chip in a mixture of light emitted diode E scrap. What kind of signal was used for this? Secondary electron, backscattered electron, X-ray diffraction signal, phonon scattering. The correct answer here would be backscattered electron. So backscattered electron image gives contrast based on atomic number difference. So so GaN so gallium nitride will appear at a different contrast compared to other elements in the sample. So that is why backscatter electron is used here. Which of the following is true for the following interaction volumes? So we have two images, A and B. A corresponds to highest rating voltage, B corresponds to highest rating voltage. So the correct answer would be B.
So our interaction volume increases with increasing acceleration voltage. So since image B has a higher interaction volume, larger interaction volume, so it will have a higher accelerating voltage. Interaction volume increases. Wait, this is wrong. On what factors do the intensity of secondary electrons depend upon? Shape of irradiated object, chemical composition of irradiated object, number of electrons injected, shape and chemical composition of irradiated object, number of electrons ejected, and on the number of electrons resorbed by surroundings. So the answer to this should be D. So all of these affect the intensity of secondary electrons. SC electrons are useful for microstructure study in SEM, while BSC electrons are useful only for diffraction study such as EPSD study. True, false. So the correct answer is false. So secondary electrons are used for microstructural or topographical study, but backscattered electrons are not just used for EBSD diffraction study, they are also used for taking co- compositional contrast imaging, that is imaging with contrast with respect to composition. So hence the answer is false. Secondary electrons generated from more than 2 nanometer depth cannot emerge out of the specimen. True or false? That is correct. The answer is false. So the secondary electrons, the depth of secondary electron imaging is up to 15 nanometers. So more than here it says 2 nanometer, which is false. Depth of field of scanning electron microscope will increase when objective diameter, aperture diameter will increase, magnification increase, work work working distance increase, none of the above. So the correct answer is C. So if you increase your aperture diameter, you will increase your alpha. That will reduce your depth of field. If you increase your magnetization, that will also decrease your depth of field. But if increase your working distance, that will increase your depth of field. So the correct answer is C. And this that are all the questions I had for today. Thank you for attending. If you have any doubts, you can ask, or if you want to leave, you can leave the chat. Yes, if you have some doubt, you can ask.